Okay, let us continue the second part of today's class. Okay, we have taught to this equation. Okay, we define the maximum reward by Rmax, which is defined as the maximum of summation of small s, where small s is in capital Si, and capital Si is the finite state space of the ith channel, and 1 is smaller than or equal to I, and I is smaller than or equal to capital K, and capital K is the number of the channels. Okay, let us go back to L. And there is another symbol, lambda bar minima in L. Okay, let us see lambda bar minima. Okay, lambda bar minima is defined as 1 minus lambda maxima, and lambda maxima is defined as the maximum of lambda I, where 1 is smaller than or equal to I, and I is smaller than or equal to capital K, and K is the number of the channels. And lambda I is the second largest eigenvalue of Pi. Okay. Now let Pi is the transition probability matrix of the channel I. Okay. So we have reviewed the d bar I is defined as 4L over mu star minus mu sigma of I squared. But what is mu star and mu sigma of I? Okay, let us review these two symbols. Okay, we define the channel index permutation of 1 to capital K by sigma such that sigma star is defined as mu sigma of 1, which is greater than or equal to mu sigma of 2, which is greater than or equal to which is greater than or equal to mu sigma capital K, and the stationary reward mean mu I is given by mu I is equal to summation small s times pi I of small s, where s is in capital Si, and what is pi I of small s? Okay. The vector pi I is equal to pi I of s, where s is in capital Si, is the stationary distribution of channel I. Okay. And what is capital Si? Okay. Capital Si is the finite state space of the ith channel. So we have a review what is d bar I. Okay, so next we estimate d bar I directly by setting d hat I of t is equal to 4L over maxima j s tilde j of t minus s tilde I of t squared. Okay, we have reviewed what is L several minutes ago. Then let us review what is s tilde j of t and what is s tilde I of t. Okay, S tilde I of t is the sample reward mean of channel I that the user computes based on observations taken from Vi only at time t. Okay, then what is Vi? Okay, the set of time instants during SB2 epochs is denoted by Vi. An example is given in figure 1.3, where we executed ASR without knowing delta and by setting epsilon to 0. Okay, let us see figure 1.3. Okay, in this figure we can see that the x-axis is time from 0 to 10,000. And the y-axis is the capital R of t over log of t from 0 to 45. Okay. The regret normalized by log t, so capital R is the regret, for the RMAB channel model with 8 Markovian channels under ASR, DSEE, and RCA as a function of time. Each channel has two states, good and bad, with rewards 1 and 0.1 respectively. The transition probability vectors from good state to bad state and from bad state to good state are 0.09, 0.9, 0.08, 0.7, 0.06, 0.5, 0.04, 0.3. So there are totally 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 Markovian channels. And 0.01, 0.1, 0.02, 0.3, 0.04, 0.5, 0.06, 0.7. So there are totally 1, 2, 3, 4, 5, 6, 7, 8. 8 Markovian channels respectively. Okay, in this figure we can see that there are 3 different algorithms. The green square is the ASR algorithm, and the red X is the DSEE algorithm, and the black diamond is the RCA algorithm. Okay. So where we executed ASR without knowing delta and by setting epsilon to 0, d hat I of t was estimated on the fly. It can be seen that ASR significantly outperforms both DSEE and RCA. Okay, we can see that ASR has the lowest regret normalized by log t. When the regret is smaller, it has better performance. So ASR algorithm has the better performance than DSEE and RCA algorithms. Okay, additional numerical experiments can be found in Gaffney and Cohen, 2018 B and A. Okay, next we will go to section 1.3, learning algorithms for channel allocation. Okay, in this section we consider the more general case where multiple users share the spectrum, and the goal is to effectively allocate channels to users in a distributed manner with the goal of maximizing a certain objective. Since the focus in this section is on the interaction among users, and not between the cognitive user and external processes, as discussed in the previous section, we do not assume that there are primary and secondary users in the networks. For example, E.G. means for example, as in the open sharing model for DSA, Zhao and Sadler, 2007. Let us see this reference. Zhao and Sadler, a survey of dynamic spectrum access, which is published in IEEE Signal Processing magazine in 2007. Nevertheless, what is nevertheless? Let us see the handout. Page 57, problem 1. What is nevertheless? Solution. Nevertheless is an adverb. Definition of nevertheless. In spite of that, however. For example, her childish but nevertheless real delight, Richard Corbin. So in one word, nevertheless means however. Let us go back to the slides. Nevertheless, the model can be extended by adding external processes that are not affected by other users' actions to model the coexistence of primary users in the network. Let us look at the section 1.3.1, the network model. Consider a wireless network consisting of a set N, which is equal to 1, 2 to capital N, of users, and a set K, which is equal to 1, 2 to capital K, of shared orthogonal channels. The users transmit their data on the shared channels using a random access protocol. We mainly focus on Aloha type narrowband transmission. Do you remember what is Aloha? I have told to you before. Let us see the handout and search for Aloha. Aloha. What is Aloha? This is a problem on page 6. So if you forget what is Aloha, please review this problem and answer. Aloha type narrowband transmission, in which at each time slot each user is allowed to choose a single channel for transmission with a certain transmission probability. In section 1.3.2, we discuss other types of communication protocols. We assume that users are backlogged Okay, what is backlogged? That is, all users always have packets to transmit. Transmission on channel K is successful if only a single user transmits over channel K in a given time slot. Otherwise, a collision occurs. Note that in the case when capital N is smaller than or equal to capital K, okay, that is, the number of users is smaller than or equal to the number of shared orthogonal channels. It is possible that all users transmit at the same time without collisions. Okay, because each user can occupy a channel. Otherwise, a certain transmission schedule should be applied to reduce the number of collisions. Each user receives an acknowledgement signal, ACK. Okay, what is the acknowledgement signal, ACK? Okay, let us see the handout. Okay, search for egg. Okay, next, egg. Okay, here. Okay, page 59, problem 1. What is acknowledgement signal? Egg. Solution: in data networking, telecommunications, and computer buses, an acknowledgement, ACK, is a signal that is passed between communicating processes, computers, or devices to signify acknowledgement or receipt of message as part of a communications protocol. Okay, this is the ACK. Okay, each user receives an acknowledgement signal ACK after transmission to indicate whether its packet was successfully delivered. Okay, if a receiver has successfully received its packet, then the receiver will transmit an ACK signal to the transmitter. The ACK signal at time slot t is denoted by the binary observation On of t, where On of t is equal to 1 indicates successful transmission, and On of t is equal to 0 indicates that the transmission has failed. That is, a collision occurred. The action for user N at time slot t is denoted by An of t, which is in the set 0, 1 dots to capital K. We say that An of t is equal to 0 when user N does not transmit a packet at time slot t, and An of t is equal to small k, where 1 is smaller than or equal to small k, and small k is smaller than or equal to capital K, when user N transmits a packet on channel K at time slot t. Note that the actions Aj of t, j is not equal to N, which are taken by other users, are unknown to user N. As a result, the network state, that is, the entire action profile of all users at time t is only partially observed by user n through the local signal on of t, which makes the problem of obtaining efficient DSA strategies among users challenging. Okay, do you remember what is DSA? Okay, let us search for DSA. Okay, here DSA means the dynamic spectrum access. Okay, let us go back to page 61. Okay, DSA strategies among users challenging. Let Hn of t is equal to An of I, where I is equal to 1 to t. Okay, do you remember what is An of I? Okay, let us review it. Okay, the action for user n at time slot t is denoted by An of t. And On of I, where I is equal to 1 to t. And what is On of I? Okay, let us review it. Okay, the X signal at time slot t is denoted by the binary observation On of t, where On of t is equal to 1 indicates successful transmission, and On of t is equal to 0 indicates that the transmission has failed, that is, a collision occurred. Okay, be the history of user n at time slot t, which is the set of all its past actions and observations. Okay, because it is the history, so we use the letter H to denote the history. And An of I is the past actions, and On of I is the past observations. A strategy sigma n of t of user n at time slot t maps from history Hn of t minus 1 to a probability mass function over actions 0, 1, dots, capital K. Thus, sigma n of t can be written as an 1 by capital K row vector. Sigma n of t is equal to Pn0 of t and Pn1 of t and dots Pn capital K of t. So it should be, strictly speaking, sigma n of t should be an 1 by k plus 1 row vector, because there is an 0 here. Okay, where Pnk of t is equal to the probability of An of t is equal to small k, is the probability that user n takes action An of t is equal to small k at time t. The time series vector of strategies is denoted by sigma n, and sigma n is equal to sigma n of t, where t is equal to 1, 2, and so on. The strategy profile of all users and the strategy profile of all users except user n are denoted by sigma is equal to sigma I is equal to 1 to n, And okay, it is 25 minutes. Let us take a break.